My mouse is very, very laggy. This is going to be
Oh,
challenging.
okay.
Maybe I just won't use the pointer.
Okay. Good day to everybody, and you're welcome to today's colloquium that will be delivered by Professor Sossina Haile. She's the Walter P. Murphy Professor of Material Science and Engineering at Northwestern University, a position she assumed in 2015 after serving 18 years on the faculty at Caltech. She earned her PhD in Material Science and Engineering from MIT 1992. Her research broadly encompasses materials, especially oxides, for sustainable electrochemical energy technologies. Her work in fuel cell science and technology has pushed the field to new heights and record performance metrics. In parallel, she has created new avenues for harnessing sunlight to meet rising energy demand and demonstrating viable solutions to the challenge of hydrogen today. Among her many awards, in 2008, Professor Sossina received an American Competitiveness and Innovation Fellowship from the US NSF, National Science Foundation, in recognition of her timely and transformative research in the energy field and her dedication to inclusive mentoring, education, and outreach across many levels. In 2010, she was the recipient of the Chemical Pioneer Award by the American Institute of Chemists. In 2012, she got the International Ceramics Prize by the World Academy of Ceramics. In 2020, she got the Campbell Lecturership by MRS. She's a fellow of the Material Research Society, the American Ceramic Society, the Royal Society of Chemistry, the African Academy of Sciences, and the Ethiopian Academy of Sciences. And she serves on the editorial board of JUL and MRS Energy and Sustainability. Professor Sossina also currently serves on the DOE Basic Energy Science Advisory Board. She leads the Joint US Africa Material Initiative, JAMI, and she's a member of the AMRS Board of Directors. She has been doing a lot of work in Africa um, and also connecting people from the US and Africa. And we are happy to have her here today, where she'll be talking to us about advancing the science of oxyanion-based superprotonic conductors. Thank you very much, Professor Sossina, and over to you.
Okay, thank you, Dr. Amalulu, for the very kind introduction. I hope you can hear me well and see my screen well. I'm very pleased to be able to talk to you about what we do in oxyanion superprotonic compounds and how we use them for advancing electrochemical technologies. Let's see. My screen has decided to freeze. Okay, well, it's very, very laggy. Okay, extremely laggy. All right, I'm going to stop the laser pointer and not use it because that I think is creating the lag. Okay, well, it's not responding. It's responding slowly. Apologies for that. Hopefully we can get through my slides. All right, so let me tell you what superprotonic solid acid compounds are and how they are electrolytes. They are materials that are intermediates between a normal salt, such as cesium sulfate, and a normal acid, such as sulfuric acid. You put the two together and you get a compound like cesium hydrogen sulfate, which has protons in the crystalline structure. So it's a solid material, but it has acidic protons. And we're interested in these materials because they have transport properties that rival those of liquid acids, in some cases even being more conductive of protons in the solid state than when we actually melt them. So that's really phenomenal ability of these materials to transfer protons very quickly. Yet they provide the benefits of being the solid state, so you can use them as a structural component without having to encapsulate them. And the material cesium dihydrogen phosphate is the one that we've used in several devices, including fuel cells, hydrogen generators, hydrogen pumps, and so on. And what you can see on the right side is a schematic showing the behavior of the conductivity as a function of temperature. So this is shown on an Arrhenius plot, meaning temperature is increasing to the left. I think it's still your left, certainly my left. And we go through a structural transition from having a normal crystal structure to a disordered structure where we have this high conductivity. There are many applications, as I alluded to, for these devices, one of which is in a fuel cell. And a fuel cell here, as we see it, has the proton conducting electrolyte. And we are bringing in hydrogen at the anode side and bringing in air at the cathode side. And the behavior then that we characterize, I think that this is the wrong slide. I'm going to end the show for a moment. Yep, no, this is right. Okay. Let me see if I can get the animations to respond. Okay, still a little slaggy. Okay, all right. So the way that we use this in a fuel cell is bring, as I said, the hydrogen at the anode, the air at the cathode side. And just to show you the typical behavior that we get from this fuel cell, we are achieving peak power densities on the order of 200 milliwatts per centimeter squared. Perhaps a little bit hard to put that into context for you, but I'll show you that this is, well, this was perhaps competitive with the levels that phosphoric acid fuel cells were at the time that they were being deployed into commercial fuel cell buses that were, going to sort of clean up all of our cities because we didn't want to have diesel buses anymore. So it works. That's the main point that I wanted to show you here. Our anode is particularly effective. The platinum loading in the anode is moderate, 0.25 milligrams per centimeter squared. The platinum loading on the cathode side is not moderate, it's quite high. And our cathode is also the one that has longevity challenges. So that's the side in terms of the device improvements. That's the side that we're working on. And I'll show you that it's connected to the electrolyte behavior. So that brings us to designing better electrolytes to allow the cathode functionality to improve. Because our anode is so good, we can do more interesting things than just simply providing hydrogen. And we can, for example, use this in a direct alcohol fuel cell. And methanol, for example, is, I've shown you here the way that you can use methanol in a fuel cell that has a proton conducting electrolyte. You generate the protons by reacting the methanol with steam, either directly an electrooxidation reaction or by having a steam reforming reaction that produces hydrogen and CO2, and then the hydrogen gets electrooxidized at the anode side. Both of these, of course, produce CO2 as products, which we don't want to have. And what we are relying on is the fact that methanol is a bioproduced fuel, so the CO2 would be recycled. What we see here is the way that we do it is we put in a reforming catalyst to allow the methanol to do that first step, which is to react with steam to produce either directly protons or produce hydrogen. We suspect that it's a two-step reaction where we're producing the hydrogen first and then that gets consumed at the anode. And there's a very good thermal match here in the sense that the endothermic reaction of the fuel cell, so it is releasing heat because it's not 100% efficient, and the exothermic reaction of the reformer that it requires heat. I think I've wrote them reversed, sorry about that. So the reformer is endothermic, it needs heat, and the temperature is well matched. So this works very, very well. And here's an example of our fuel cell operating directly on methanol. We can see that the hydrogen performance, as I showed you before, the peak power density is around 300 milliwatts per centimeter squared. And when we supply methanol, the peak power density is about 85% of what we achieved with hydrogen. In polymer fuel cells, the main competitor for ambient temperature fuel cell operation, that differential is very large, where the direct methanol fuel cells only achieve about 10% of the power output of the hydrogen fuel cells. That's because there's a lot of methanol crossover on the membrane, and you have to dilute that methanol extensively, whereas in our case, there's no methanol crossover, so there's no dilution required. And another alternative fuel would be ethanol. And here we see that not only we can use ethanol, but if you ran out of lab quality ethanol, you could actually use vodka as well. So that works. It's about the same concentration of ethanol to water in vodka as what our fuel cell requires. Another technology that we've exploited with these electrochemical devices is to employ hydrogen extraction from liquid carriers. And what this does for us is that means that we are able to, like I said, do interesting things with the anode side. And an excellent liquid carrier of hydrogen is ammonia. And it is a good carrier because the product is just nitrogen. There's no CO2 that would need to be recycled. And so we introduce a reforming catalyst, very similar to what we did with our direct methanol and direct alcohol fuel cells. And the difference here now is that we're evolving hydrogen. So we're using this device to break up the ammonia into nitrogen and hydrogen. And the hydrogen is going to then be used in for example, a polymer membrane fuel cell, which operates at lower temperatures and is easier to use in an automotive application. So the advantage here is that we replace that difficult cathode material with our hydrogen evolution cathode, which allows us to lower the platinum loading and design the electrode structure in a way that provides greater stability. So these devices operate much better in terms of the long-term degradation than our fuel cells. And the way that we put this together, we needed a reforming catalyst. The one that we used was one that was already reported in literature. We synthesized it ourselves, which is ruthenium on carbon nanotubes with additional cesium, which seems to change the electron density on the ruthenium and enhance its activity for the ammonia decomposition. We put that together, and we then create a cell where we are supplying ammonia and extracting the pure hydrogen out of it. What you can see on the left is the current density as a function of the voltage that we apply. And from that current density, you can calculate the hydrogen production. And we also measured the hydrogen production directly using mass spectrometry, and we could confirm that the hydrogen production was exactly equal to the number of electrons that we delivered, and that tells us that our system has 100% Faraday efficiency. This does not mean that it has 100% energy efficiency. It means that for every electron that we deliver, we achieve one hydrogen ion going across our electrolyte, and we have no parasitic reactions. We didn't expect to have any parasitic reactions, but that was a nice confirmation. And looking to the right, we see that if we compare the hydrogen that is generated per mole of catalyst, it is quite high compared to traditional methods of decomposing ammonia into hydrogen and nitrogen, which is to flow the ammonia past a packed bed catalyst. And those reactions happen at much higher temperatures. So you can see that sort of in the gray area. Those are all the typical results using packed bed catalysts. And in that case, because the ammonia, residual ammonia is is still combined with the hydrogen and the nitrogen, you then have to follow that with a hydrogen separation, hydrogen purification step, whereas in the electrochemical process, the hydrogen is already pure. There's no residual ammonia that's in it. And additionally, we can pump it electrochemically so that one could automatically have pressurized hydrogen, whereas again, if you use a packed catalyst bed, you have to separate it and then have another device to pump the hydrogen, which is what you normally do if you put hydrogen into a tank, you're not going to use it at 1 atmosphere. You're going to pump it up so you have, some reasonable number of hydrogen molecules in your tank. So this was great. And I'll also say that we also demonstrated using our mass spectrometry that there was no nitrogen oxides being produced, so no NOx generated, which is important also from the perspective of the clean environment. So I've shown you then that the motivation for using these superprotonic electrolytes is that they have a lot of applications in electrochemical devices. And I didn't want to make this presentation very much about the devices per se, but really to give you the idea of the motivation why we look at these materials. So what are the challenges that are then connected with the electrolyte? Well, the only truly viable electrolyte that we have in our hands is the cesium dihydrogen phosphate. And I'll show you it's a good electrolyte, but it's not perfect. And there are many, many other superprotonic compounds that are reported. In some cases, the data are conflicting. And the lack of validated examples or the minimal number of such validated examples makes it very difficult to establish design principles for generating and creating, discovering, designing new compounds that have high conductivity. Computational prediction is catching up. The whole world wants to do, AI-generated solutions to materials problems. I would say that it still lags experiment. And so I'm going to tell you now a few sort of extended short stories about candidate compounds that we've looked at that show promise in these applications, but certainly give us insights as to what to try next in terms of how does superprotonic conductivity get, how can we design it, how can we predict it, how can we come up with new compounds to overcome the shortcomings of the cesium dihydrogen phosphate. Now, I don't expect you to read this, but this is the first short story, and it is about the cesium dihydrogen phosphate. When my group got involved in this a few years back, there was a lot of conflicting evidence as to whether or not this material had a true superprotonic conductivity, polymorphic change in structure that led to high conductivity. So the authors in red are those who said, no, it's not true. It's a decomposition reaction. And the authors in green are the ones who said, yes, it's true. There is really a superprotonic transition. And the one in black is one that was non-committal. Okay. So what we did was establish that, in fact, the transition competes with dehydration. And what you can see on this left is that we did a TG measurement, thermogravimetric measurement, and we changed the steam partial pressure and look at the mass loss. And there is indeed a mass loss, and you can suppress it by increasing the steam partial pressure. That's, physical chemistry, absolutely what you would expect to achieve. Now, if you compare that to the DSC signal, the differential scanning calorimetry behavior, you can see that there is a transition that is insensitive to the steam partial pressure. And followed by that is a transition that depends on the steam partial pressure. So we identify the first one as being the polymorphic transition because that should depend on how much steam is in the system. It's a solid, fixed composition transition, whereas the dehydration, which we saw already in the TGA experiment, is indeed suppressed by steam. And kind of interesting is that we see that in the TG experiment, there is a one-step dehydration that occurs at low steam concentrations and then a two-step dehydration process at high steam concentrations. Okay. All right, so we also show that if we have enough steam in the system and we do X-ray diffraction measurements as a function of temperature with this high humidification, we can clearly see the cubic phase. We have the simple diffraction pattern of that simple cubic phase, nice, few lines nicely spaced that match exactly what we expect for the cubic pattern. Whereas at the lower temperatures, we have the monoclinic phase, and we have a nice wide window of stability. So this is clearly not a decomposition reaction. We put all of the results together, and we see that there's this range, this window of which the superprotonic phase is stable. The transition temperature to that cubic phase is around 228 to 230 degrees Celsius. That's about our uncertainty in that number. And we have two dehydration reactions. One at low steam partial pressure goes directly to the metaphosphate. And at higher partial pressures, the transition is through a liquid phase first, which is then followed by a transition to the solid dehydration product. And that explains to us why we had those two features in the thermogravimetric analysis measurements. We can convert this this phase stability behavior into an Arrhenius plot and see that it behaves in a way that you expect, meaning that the lines all make sense, and we can take the slope of those lines to get at the activation the delta G of reaction for these different reactions, and even confirm the value of the superprotonic transition temperature from the change in slope between the dehydration to the solid dehydration product from the monoclinic phase versus that from the cubic phase. So it all makes thermodynamic sense, and we understand this material, and we have a very good roadmap to the conditions under which we can use it in our fuel cell. And what you see on the left is the red mark that shows the typical operation conditions for us. So we're typically at 250 degrees Celsius, maybe a little bit lower, maybe 240, and we humidify to a level on the order of 0.3 to 0.4 atmospheres. That means that it is a 100% humidification at around 70 to 75 degrees Celsius. So we pass the carrier gas, which is typically synthetic air, through a humidifier that is held at that temperature. This would be the dew point temperature, and again, around 70 to 80 degrees Celsius. It means that the material is a little bit delicate. You have to maintain these conditions to prevent that dehydration, but once you treat it well, it treats you back reasonably well. So there are many superprotonic solid acid compounds that exist. This is just the whole range of them. There are ones that go from a monoclinic structure to a tetrahedral structure, ones that go from monoclinic to trigonal, from monoclinic to the cubic, which I described to you. That's the cesium dihydrogen phosphate. Monoclinic to another trigonal, where on that fourth example, the polyanion group actually has a hydride ion replacing one of the oxygen ions, so unusual chemistry, but again goes to a cubic high conductivity phase. And then there's some other sort of messy ones that are hexagonal in structure, and the high conductivity structure is not known for those materials. A general feature is that these materials all have some alkali species, large alkali, typically cesium or rubidium, sometimes as small as the ammonium ion or the potassium ion. The polyanion group is typically sulfate or selenate, can also be phosphate or arsenate. We don't use arsenates in my lab because I don't like to deal with toxic elements. Even selenium is not a fun one to work with, but as long as it stays in the oxidized state, it's not toxic. When it gets reduced, becomes toxic, as does sulfur and phosphorus. H2S and H3P are very toxic, so we make sure everything stays in the oxidized phase. So this is a wide range of materials. And as I said, the cesium dihydrogen phosphate is the one that we typically use. So let me tell you a little bit about the rubidium compounds, these trimetal compounds. These are materials, as I said, that have a monoclinic structure and transform to a trigonal phase at high temperature. And the monoclinic structure is very similar to the trigonal phase. There's only a slight change in the arrangement of the hydrogen bonds. You can see the hydrogen bonds link on the left side. They link two selenate or sulfate units together. And at the high temperature, that hydrogen bond gets distributed over 3 different sites. And it's a double minimum hydrogen bond. So the occupancy then of the protons in those sites becomes 1,6. And there's very high conductivity in the plane because of that structural reorientation that happens in the plane. And it's a little bit more of a 2-dimensional conductor than a 3D conductor. So the overall view on these materials is that if we look at which materials have this transition, which don't, generally the increase in the cation size increases the transition temperature. It's not really clear what happens when you change between sulfur and selenium. And so we did some experiments in particular where we looked at the rubidium sulfate compound and found that it didn't actually have a superprotonic transition. So again, just sort of making sure that we understand the material set overall to be able to draw design principles from what we know. And then we looked at the influence of the cation in the selenate system. So we looked at solid solutions between potassium and rubidium, and solid solutions between rubidium and cesium. I'm going to skip this. I really do think that my slides came up with a different one that I wanted to present. So this is too much detail for this. So let me skip this. I think that this is too much detail. I want to go to this system. Which is the solid solution system between the potassium rubidium and the cesium rubidium. And what we see here is that they're make full solid solution just below the transition and full solid solution just above the transition. And I apologize that my pointer is not going to work because of the lag. But what you can see is that there is a general trend towards an increase in the transition temperature as we increase the size of the cation. So you see that fairly clearly on the potassium to rubidium side. In the case of the rubidium to cesium side, that's a little more a fixed of transition temperature, and we have a slightly different phase behavior where, in fact, at close to 50-50, we have a decrease in the transition temperature, which gives us advantages to some extent for the overall application. The conductivity we measured here, which was the other goal, was to really understand how does the conductivity change with the substitution of these cations. And what we found in this case is that having the smaller cation increases the conductivity at a given temperature. An order of magnitude is pretty significant. So that's the cesium end is close to, maybe 5 times 10 to the 4th inverse ohm centimeters, whereas at the potassium end, we're, above as again, an order of magnitude higher. So that's pretty significant. And it suggests to us that we could exploit a similar approach to improving the conductivity of our cesium dihydrogen phosphate. Let me just also connect this to something that's called a Meyer-Nandel correlation, which is a correlation between the pre-exponential of the conductivity and the activation energy. And these tend to be correlated in many instances and many phenomena. And it has been somewhat explained by saying that if you're trying to get over an activation barrier for conductivity, if you have a higher vibrational state, and more vibrations, you're higher up in the energy potential well. So therefore, the more entropy you have, the more vibrational entropy you have, effectively the smaller the barrier, even though the energy landscape may be the same. You're starting at a higher position because of that vibrational entropy. And that would be the explanation for the correlation between these two. It's not I mean, I would say this is still very much an open discussion, but that is one potential explanation for why these two parameters are scaled together. So we have a smaller activation energy when we have a smaller cation, and that gives us ultimately the higher conductivity, even though the pre-exponential term is lower when we have more potassium. All right, so let me go back now to the cesium dihydrogen phosphate system and look at this family overall. As I said, we wanted to look at the influence of replacing some of the cesium with rubidium or some of the cesium with potassium, sort of motivated, as you might expect, by this behavior in the selenate compounds. And there's a lot of disputes here about what's true and what isn't true, so we'll just leave that as that. So let's look at these two systems. When we made this system between cesium dihydrogen phosphate and rubidium dihydrogen phosphate, we were somewhat disappointed because the transition temperature increases monotonically. So there's no sort of minimum behavior as we saw for one of our previous systems. And very unfortunately, the dehydration temperature decreases. So that means the window of operability is getting narrower and narrower as we increase the rubidium concentration. So thermodynamic stability was not favorable in that case. Looking at the potassium system, the phase diagram is a little more complex because there's not complete solid solution between cesium dihydrogen phosphate and potassium dihydrogen phosphate. That makes sense because potassium is substantially smaller than cesium, but there is a window of the cubic phase. Again, the dehydration temperature decreases as we increase the potassium, which is unfortunate, but the superprotonic transition temperature does decline. So the window of operability is moving downwards and slightly narrowing. So the thermodynamic impact is not as negative in the case of the potassium as it is with rubidium. But we thought, okay, let's see what the influence is on the conductivity, because that's where we hope to gain some positive response. And unfortunately, the conductivity did decrease, opposite of what we just saw with the previous results. We do have a similar Meyer-Nandel, it's so hard for me to say, Nandel correlation. So what you see on the conductivity result is that the activation energy declines with increasing dopant, but the pre-exponential declines. And in this case, the pre-exponential is the dominant factor that makes the conductivity decrease more at the temperature of interest than it did in the previous case. So even though we have a very similar correlation, it's where we are in this correlation relative to the isokinetic temperature, basically, that we are seeing this unfortunate decline in conductivity. And you might ask, can this be correlated in some way to the crystallography of the materials, to the crystal chemistry? Because, of course, as you introduce these smaller dopants, the lattice constant decreases. And we cannot attribute it directly to an overall change in the unit cell volume. The unit cell volumes between the 10% potassium doped and the 19% rubidium doped are similar. You can see that on the right side plot. Yet the difference in conductivity is quite significant. So it can't be just explained by the change in cell parameters. And we would have expected, for example, the 50% rubidium to be significantly worse than the 10% potassium. Again, if it were all just about the macroscopic change in the unit cell, whereas the 50% rubidium is substantially more conductive than the 10% potassium. All right, so we still have an open question there where we're trying to understand why do these substituents have sort of differing impacts on the overall conductivity. In one case, these small cations increase the conductivity, and in the case in our stable material that we really like to use, the conductivity declines. All right, so we went to another case saying, well, let's look at ammonium substitution for the cesium, because ammonium, potentially we have ways to move the proton via that alkali ion site, because we've now got the NH4 ion in addition to the H2PO4 polyanion. So maybe that can improve the overall conductivity. So that was our goal. Trying to make the conductivity, the compound that you see on the right of the first equation. What we discovered was that when we heated this material up to try to do the conductivity measurements and the thermal analysis, that the ammonia, the NH3, evolved from the compound, and we were left with a material that was cesium rich, cesium deficient, and effectively proton doped. Now, we would have never tried to substitute cesium ions with protons because the size difference is so immense. Yet that's effectively what we created when we attempted to do ammonium ion doping. After recognizing what was happening, then we went ahead and did direct synthesis of proton substituted or doped compounds using cesium dihydrogen phosphate and this cesium H5PO4 compound, which allows us to then create materials or compositions anywhere in that range, in that X value, so that we can increase the proton content and decrease the cesium content sort of to arbitrary values by making mixtures of these two compounds. And along the way, we further discovered that there is a new compound which appears at a 5-to-2 stoichiometry between these two solid state reactants that we put together. And it creates for us a compound that we name heptacesium tetrahydroxyphosphonium octadihydrogen phosphate. And that is a mouthful. So we refer to it as CPP. And as you look at the in situ X-ray diffraction results here, you can see that at room temperature, we have a mixture of those two precursors. And then as we go to 110 degrees Celsius, we get a pattern that looks very similar to our cubic cesium dihydrogen phosphate pattern, but it has a number of superstructure peaks. And we also see in the DSC plot that there's a transition to this new phase. Okay, great. So we have this 4x4x4 superstructure that we can index. And we then grew, my very amazing student grew this compound at high temperature above that transition that happens at 90 degrees Celsius, pulled it out of the aqueous solution and ran it over to the single crystal diffractometer and made sure that it stayed hot during the X-ray measurement, and then was able to solve the structure. And we can see the superstructure arrangement where 1 in 8 of the cesium cations is replaced by a effectively an HPO4 positive cation. So we have many polyanions in this structure. Those are the ones shown in yellow. And they're disordered. That's why they don't look like tetrahedra, but structurally they're tetrahedra, but they exist in many different arrangements. And what you see in blue are these phosphate groups that are effectively polycations. And again, they are tetrahedral units, but because they're undergoing this reorientation, they look like these funny shapes for the polyhedra. And we can see in the NMR results that when we are when we have this structure, that we can see the proton NMR peaks for the polyanion groups. They overlap significantly. They're not resolved. And then the two polycation groups have their proton signals as well. And we can't differentiate all the different types of protons in the system, but I'm sorry, these are the the phosphorus NMR. So we can see the phosphorus shifts, and we can't distinguish the two different phosphorus groups, the P3 and the P4, which are the polyanions, but we can distinguish the two phosphorus that are the polycation groups. And I thank my collaborator, Yan Yan Hu at Florida State University, where the National High Field National High Field Magnetic Laboratory is for helping us collect these data and analyzing the results. Unfortunately, the conductivity is an order of magnitude lower than that of the cesium dihydrogen phosphate. Maybe not so surprising because the conductivity at which this compound we measured it is a little bit lower. Well, then we increase the temperature on this material, seeing, what's its dehydration behavior. So we see a dehydration result. But what we also saw when we increased the steam partial pressure is that it has another phase transition. This was quite surprising to us. And we put this all together and noticed that there's a very small sliver of a new phase that you can see at that high steam partial pressure. That's what that second transition is when we first go through well, I'm not showing on here. We have first the transition to the formation of the CPP phase, and then that black dotted is where we transition to a new solid state, which occurs at 180 degrees Celsius, and then the dehydration occurs. And we collected then the diffraction data at 180 degrees Celsius under very high steam, and we can see that now all of those superstructure peaks are lost, and we have a pattern that looks exactly the same as cesium dihydrogen phosphate, which tells us now remarkably that there is solid solution behavior between cesium dihydrogen phosphate and effectively phosphoric acid. And we put together the phase diagram, and we see that there is a wide range of the region which has this behavior. So I've shown you the X-ray diffraction data for the CPP and the DSC results for that. And just to show you the diffraction results at the eutectoid composition, we clearly go to the cubic phase at very low temperature. This eutectoid transition is at 155 C, so we can see the cubic pattern forming at 160 C very nicely. And as we go to higher compositions of cesium, then we have this region here where we have a two-phase system, and the monoclinic cesium dihydrogen phosphate slowly gets consumed, and the cubic phase slowly increases in content. Okay, so this is our unusual phase diagram. Let me skip this part also in the interest of time. And slow. This is basically how we're proving essentially that we have some of the cesium being replaced chemically by protons, but overall the protons are surely forming part of the polyanion groups. And we can see a big change in the lattice parameter as a consequence of being cesium deficient. Okay, but let me skip that. And the conductivity in this case is attractive. So we see that this is linear temperature, not an Arrhenius plot, we can see that when the CPP compound forms, we have a small jump in conductivity. And then when we go to the solid solution phase, we have another higher temperature jump. That's at the eutectoid temperature of 150. And we get a much wider range of high conductivity behavior that we can utilize and exploit in our materials. We can use this off stoichiometry actually as a material design tool now. We see that in addition to this alkali deficient cesium dihydrogen phosphate, not yet reported, we have an alkali rich side of the cesium dihydrogen phosphate. And similarly on rubidium dihydrogen phosphate, we can also observe an alkali rich side, which then in both cases decreases the transition from the monoclinic structure to directly the cubic phase or a mixture of cubic plus monoclinic. So again, that's displaying eutectoid behavior, and controlling that eutectoid temperature will be, I think, the new way that we go forward to try to create materials that have high conductivity at reduced temperatures and therefore less of a need for humidification. And that humidification creates a lot of problems in the ultimate fuel cell application. Okay, so again, I think my uploading between SharePoint and OneDrive put the wrong set of slides here. So the summary is really about the selenate system, where we have a Meyer-Neldel correlation, which we thought would ultimately mean that always, if you have the smaller cation, you get an increase in conductivity. But in the cesium dihydrogen phosphate system, we saw that as we introduced the smaller cations, in fact, we have the opposite behavior, even though we still have a Meyer-Neldel correlation. And now we're using proton doping as a design tool, as we saw in the cesium case, where we could have cesium deficiency and increase the proton content, and even have the reverse occur as well. So with that, I want to thank you for your attention. Thank my many students who contributed to this. Some of the more recent work was done by Grace Zhang, who is now actually just defended her PhD, so she'll be walking in commencement ceremonies on Monday. Former student Louis Wang was also responsible for a lot of this work, and some of the early work on the devices was performed by Callan Chisholm, Dane Boysen, and Tetsuya Uda, and thank you for your attention.
Okay, thank you very much, Sossina. Thank you. Yeah. There are quite a lot of questions in the chat. Okay. So I think the first thing is if you ask a question in the chat, you could unmute yourself and ask your question again. So this will be the way we start, and then later on we can go through the chat to see if the other questions we didn't take. So if you ask a question before in the chat and want to, then you can unmute yourself and ask. At the same time, I will go through the chat to see specific questions. Any questions? So you could unmute yourself and ask.
All right. Well, I see one question, which was, have you tried this electrolyte for supercapacitors or battery devices? So for a battery, it would have to be a hydrogen battery, where it is you need to have a way to store hydrogen. I mean, there are some things that you could do with that, but basically, you have to run it reversibly. So as a supercapacitor, I don't know if it would work. So again, you'd have to have it at high temperature and humidified. So I'm not sure. I mean, that's basically why we haven't really tried in that direction. So thank you for that question.
Okay.
Please, let me ask you a question. So if you use potassium instead of, if you use sodium instead of potassium, then the structure is not stable, right? Or because we expect that if you use sodium, then the conductivity is higher.
Uh, well, we saw that in the cesium dihydrogen phosphate, we saw that introducing rubidium decreased the conductivity, introducing potassium decreased the conductivity a lot.
Okay.
And if we introduce sodium, I would expect the decrease to be even more severe. On the other hand, sodium is actually not very soluble, so we have tried that.
Oh, okay. Okay. Thank you.
It's just too small to be in.
Okay. Yeah. Peter has his hand up. Peter, welcome. Can you unmute yourself and ask?
Yeah, Sossina, thank you very much for a very interesting presentation. Can you hear me?
Yes.
Yes.
Okay. So it's very interesting to see the effect of the cation substitution, and I was just wondering, for typical solid electrolyte, it's been described in terms of the change in the molar volume of this material, which enables maybe the ions to move faster because you have a change in the activation energy. So I don't know. So it's also very interesting to see here you have some kind of counter effect. Can you really explain this, maybe relating to the structure that you obtain?
Yeah, I mean, so molar volume was the exact thing that we gravitated to first. And what we saw was that there was no correlation, right? If we compare the potassium doped and the rubidium doped, the potassium does not change the molar volume very much when it's only 10%. And yet it has a huge decrease on the conductivity compared to rubidium. So let me, I don't know, it'll take forever for my slides to go back. But what we saw is that these were not correlated, basically, because that was the thing that we immediately wanted to check.
Okay, I missed part of it because I was in another meeting, but what about the change in activation energy in this case? Is the activation energy change or is just basic?
Yes.
Okay.
Yes. So the activation energy changed. Oh, God, this is so slow. It's going to make me crazy.
Maybe you can start your mode and then just go to the.
Yeah. So the activation energy changed in a way that, oh, this is wrong. I don't know how that came. The activation energy changed in a way that we got the Meyer-Neldel correlation that both the pre-exponential and the conductivity change in a correlated way. But in the case of the phosphate materials, we were on the sort of the wrong side of the isokinetic temperature, such that at the temperature of interest, that meant that even though the activation energy is decreasing, the conductivity is decreasing, because of the pre-exponential decreasing. In the case of the selenates, we're at other side of the isokinetic temperature, such that when the activation energy decreases, even though the pre-exponential is also decreasing, we're getting a benefit for conductivity.
Okay, very interesting. I'll read the paper up, but maybe one last comment from me is also, is there also any correlation to the stability of these materials?
Yeah, so the stability in the case of the rubidium and potassium doping, the phosphate, it declined for both of them in terms of that dehydration stability. So it wasn't as if, there was no benefit. Yeah.
Oh, okay. Yeah. Thank you very much. Yeah.
I know, very frustrating for me.
Well, I still have some questions, but let me give room to other people and I can come back to you later. Yes. Thanks.
Okay. Hello, doctor.
Yeah. You can unmute yourself and ask questions. Thank you.
Okay. Hello, doctor.
Yeah. Naga, go
Okay.
ahead.
Yes, I am Naga. I have one questions for your presentation. First, thank you very much for your time and your dedication. So I have understand that recent or research developments have made in the field of superprotonic solid acid compound for sustainable energy technologies differ from other worker. So are the industry where this compound be particularly beneficial?
Yeah, I mean, there are applications. So right now, if we could make the cathode better, I think there would be much more industrial interest.
Okay.
And making the cathode better means reducing the steam requirements because the steam dilutes the oxygen that we supply to the cathode. So
Okay.
I've had a startup company in my lab that's been making these commercially. And every time it seems like there's going to be a big order, something happens in the economy that makes it, that pulls the rug out from under us, as they say. Yeah. So, you know, we can do direct methanol fuel cells very, very well. And that works extremely, extremely well, and much better than, you know, you cannot operate a solid oxide fuel cell at these low temperatures. So that means you get a lot of cost savings from the auxiliary components compared to solid oxide fuel cells. And I do a lot of work in solid oxide fuel cells, so I'm very familiar with that piece. And you cannot do direct methanol with polymer electrolyte membrane fuel cells. As I said, the methanol crossover is just a significant problem. So in that arena, these are the best fuel cells available. So it depends. If we think we can solve the hydrogen problem, then we don't really need direct methanol fuel cells. But I have not yet really seen the hydrogen delivery be, you know, overcome.
Okay. Okay. Thank you.
Yeah. Christian has his hand up. So Christian, you can unmute yourself and ask.
Thank you, Professor Haile, for this right talk. My question is about how do you think about the cost of a crystal refinement for its LD?
How do I
What do you
think
think
about
about the cost? The
about the
cost.
costs?
Yeah.
The
Is all your work done experimentally, or there's a part we are done computationally or simulation? In this case, which software, which code have you used, for example, and which property have you complete, for example? Do you think that it's easy for us to have experimental tasks or computationally tasks with the improve of computational tool like machine learning and artificial intelligence?
Yeah,
Okay,
actually,
so
Sossina, go ahead, Sossina. Go ahead.
yeah, so sort of two questions. One, which was, is this experimentally costly to study these materials? These materials are relatively inexpensive. You know, sulfuric acid, phosphoric acid, the salts, and they're actually very easy to synthesize. It's just aqueous solution. Computationally, I've collaborated with colleagues who do DFT, you know, simulations to try to predict new compounds. I did mention at the beginning of the talk that I just don't yet see that the computational prediction is faster yet than the experimental discovery. There are a lot of things that we discover somewhat accidentally, which I described with the ammonia substitution, that if you're not thinking about what all could be predicted, you just can't capture it by computation. The other part is that the phase transition behavior, I do not yet have a computational colleague who is willing to tackle that problem. Hydrogen bonding, subtleties of that, and predicting the temperature and predicting dehydration behavior, no one's tackling it. The people who do computation are interested in the dynamics of the transport behavior, which can be captured, you know, with ab initio AMD and machine learning AMD. And I have a great collaboration with Boris Kaczynski at Harvard, looking at these features. We have a computational paper with Bilge Yildiz at MIT trying to do predictions, but the predictions of new compounds were, again, did not exceed what we could do experimentally. Yeah, so experimentally, very, very low cost to synthesize these materials, very easy. Sometimes have high school students in my lab help with these experiments. Easy to make a mistake as well. So you have to be sophisticated in your interpretation, if not sophisticated in your experimental methods.
Thank you. Let me ask
Professor.
one more question. Please, let me ask a follow-up question to what Christian asked. So for the beginning, you showed us some work where they are trying to determine whether the transport is supersonic or not. I assume that there are computational molecular dynamics.
Those were all experimental studies early on.
Okay.
And because that was before MD and all the computational methods became possible. Now there are plenty of computational studies looking at the transport dynamics. And as I said, we're also working with Boris Kaczynski at Harvard to look at that. But you can't differentiate between a phase transition. You can't say a material is not decomposing just because you did a computational study of the transport, because you don't allow for decomposition in the simulation. It's very hard to have that sort of bond breaking and dehydration behavior predicted in any MD simulation.
Yeah, correct. So, a practical question. So, you have a fuel cell, methanol fuel cell. So you can use it forever as long as you put it methanol. There's a catalyst to help you generate it.
Your sound is going in and out. So what's
Sorry,
the
I wanted
question?
to ask, if you have a fuel cell, methanol fuel cell, how long does it last before it stops working when it is supplied to methanol?
Yeah, as long as you supply the methanol, it's fine. I mean, we do have some degradation on our cathode side. But it's a pretty slow degradation. So, tens of thousands of hours would, and it has nothing to do with the fact that we're supplying methanol. It has to do with the fact that the air electrode, the cathode, has some stability issues. Basically, the platinum corsins and things like that.
Thank you very much. Somebody else has a question that I was about to ask a question and asked just now. You can unmute yourself and ask.
This is going to have to be the last one for me because I have a 10 o'clock that I'm actually hour now that I'm late for. So sorry.
Okay, any other questions?
Yes, I do have a question too. But
yeah, go
now
ahead.
it's one question only allowed.
Yeah, go ahead. Go ahead.
I don't know. I think two people showed up. May I go first? All right, thank you.
Yeah.
Prof. Haile, thank you for your presentation, for your expertise. I've met Prof. first, that was in Senegal, I think before last year, and we've seen your great work in terms of developing materials for fuel cells applications. I was just curious to ask this because recently my visit to Germany, I realized that there's a lot of work being done in that place concerning biomass conversion. And so they are producing pyrochar or hydrochar, depending on the process they use. But the application of this product was mostly being focused on water cleaning as well as soil amendment. I was just curious if it's possible to try to come up with anything to do with using carbon for electrochemical cells, in the way that then the biomass conversion would have another direction where instead of combustion, rather electrochemically, it would be utilized to harness energy. If it is something that Prof has done before, or maybe you'd consider in the future, I'm really very interested in that. And I would really seek your collaboration because currently I'm doing also a biomass conversion.
Yeah, so there are direct carbon fuel cells. These are solid oxide fuel cells. Basically, carbon cannot be easily oxidized at these low temperatures. So, and then you have to be sure, of course, to capture the CO2 and think about how you recycle it. So that's my quick response to you, that our temperatures are just too low to do carbon oxidation. Yeah. So, okay.
Okay, thank you, Prof.
Yeah, thank you very much. I think if other people have questions, they can connect with you by email. And we are happy to have you. Can I share your email with the group?
Yeah, and you know what? You type my name in Google, it comes up right away. So
Okay,
you just have to be like 5 minutes of independent researcher.
Thank you very
Okay.
much, Sossina. We're grateful.
Yeah, my pleasure. All right.
Thank
Thank
you
you
to
for the
everybody. Yeah,
invitation.
thank you.
Okay.
Yeah,
Take care.
bye.
Bye-bye.
Yeah.